Our final presentation this morning looks at various application factors that influence pesticide efficiency, and we welcome Tom Wolf back to the conference. Tom is a spray application specialist based in Saskatoon. He grew up on a farm in Manitoba and studied agriculture at the University of Manitoba, the BSA, MSc, and the Ontario State University, PhD. Tom has 35 years research experience in spray technology, starting with AAFC in 1989, and now as a private consultant. With Jason DeVoe, Tom now hosts and writes the world's #1 sprayer website, sprayer101.com. He's a past, present, and fellow of the Canadian Weed Science Society and has been named Distinguished Agrologist with the Saskatchewan Institute of Agrology.
Great. Well, thank you for the introduction. I always have to laugh at the Sprayers 101 comment. You know, somebody once said, we think you're the #1 sprayer website in the world because you're the only one, and so we put that in the bios, and so it's probably true. But I do want to say something about our website. Jason DeVoe and I are doing this for free. It's funded by you. It's funded by the commodity groups. Mostly of Western Canada, but it's check-off money. And we don't accept any commercial money. Lots of nozzle and chemical manufacturers would love to sponsor us, but we don't take that. We just use the money to develop content. And so we write for you. It's written in a layman's language. It's on a scientific site. It's a site that's supposed to help you do a better job spraying. And hopefully you'll find it useful if you haven't already gone there. So just please use it. And if you have a question, on the website, Jason is spray guy, and I'm nozzle guy. Easy, right? You'll never get that confused, right? But you just click on the link and we get an email. Write us if you have a question, and we'd be happy to answer it. So, all right, the most of this is going to be about nozzles. The nozzle is the cheapest and the most important part on the sprayer. A sprayer nowadays, if you buy a loaded Agrifac, I heard there was one at the potato conference a couple weeks back, with the AIC Plus, that's $1.2 million. John Deere's, even the 616s are touching close to $1 million with all the bells and whistles. So these sprayers are unbelievably expensive. Nozzles are still $10 each. They've been that price for a very long time. And since the 1970s, when we started spraying on our farm, you know, they were $2 or $3. I mean, they haven't increased that much. Our sprayers back then were $10,000. Now they're $1 million. That's a big increase, but the nozzles haven't really changed. And you know, what determines the quality of the job? It's the nozzle. The nozzle determines your droplet size, your distribution, boom height, all these kinds of issues. That's the determining factor of your quality. So we'll spend a bit of time talking about them. So in our research that we've done over the years, we have abandoned any effort to spray really fine. A lot of our initial work was across the country, where we looked at how coarse can you go. Because there's value in going coarse. The value is that you get wind protection, you get drift protection, you get opportunities for spraying at the right time with that. And the results for grassy targets and the modes of action that target grassies, for the most part, go hand in hand, were that you could go approximately to the coarse to very coarse boundary without seeing any problem. You could go quite coarse, surprisingly coarse, with these nozzles. So the air induction technology, when used properly, was good even for these difficult situations. On broadleaf targets, it was even easier. So on broadleaf targets, we could go to the boundary between a very coarse and extremely coarse. We could go coarser than we ever really thought we should. And it still surprises me to this day when we do trials and we go out with sprays that I think are quite coarse, and yet the results are quite good. Now, there is a bit of a word of warning, and that is that increasingly we're tank mixing contacts and systemics for the purposes of resistance management. And it's always the most limiting factor that is going to be dominating. So if we're doing a tank mix that targets both grassy and broadleaf weeds, and we're doing a tank mix that uses both systemic and contact products, which is very, very common, we're going to have to default to the most limiting factor, which is the slightly finer spray. And so the drift protection isn't going to be as available for us. So those are kind of the lessons that we learned, and they hold true. Pesticides, herbicides in particular, are particularly robust systems. They withstand a fair bit of misuse, to be quite honest. They're a terrific technology, so let's take advantage of it, go as coarse as we can, protect the environment, and open more hours per day of spraying, which is really what's important to do the right job. What do these nozzles look like in terms of droplet size? So we had a laser at Agriculture Canada when I worked there, and this is some data that we developed for 3 different varieties or different spray qualities, and I just want to show you what these look like. So the first thing we do is we look at the distribution of the droplet sizes in the spray pattern. And on the x-axis here you see droplet size. It goes up to about 1,000 microns. On the y-axis on the left side, I'm just looking at droplet number. And all sprays look like this. They have sort of a log normal distribution, which means the majority of the droplets are small, and then fewer and fewer are larger and larger. And now we can convert this. Now look at the number. The top number here is 5,000 on the y-axis. I want you to just make a mental note of that number. That's a medium spray quality. We convert that, we multiply, do some math, and we figure out what is the volume in that spray. So that's 4/3 pi r cubed is the volume of a sphere, and we multiply it by the number of droplets, and so we get a volume distribution. And now we have something very interesting that we can do. We can look at where the volume is. So this is the driftable size fraction, less than 150 microns, and we want to avoid that because that gives us problems with drift. And then on the right side, the droplets larger than 600 are the ones that are more likely to bounce or not hit the target in the first place because of their low relative, frequency. So we want to avoid those. And then the middle part that I haven't colored in is really the usable size fraction, or the volume. So you see there's a fair bit of the spray is actually in there, so that's very good. Now, if we go to a coarse spray, this is the second one of the 3 we'll do, let's look at, first of all, the number distribution. The shape of it is identical. The majority of droplets are small, so we always have small droplets. But the number of small droplets has been cut in half. Okay? Now, when we convert that to a volume, it looks like this. You notice it shifted a little bit to the right compared to the previous one. If we look at the drift protection, it's better. We've cut drift by at least a factor of 2. But we're starting to see a small increase in the volume that is in large droplets where we see some loss of efficacy or efficiency at least. Extremely coarse sprays. We can overshoot this mark. Let's look at this one. This is now the number distribution of an extremely coarse spray. Shape's the same. The majority of the droplets are small. There are small drops in all of these sprays. But look at the number. It's 600 now. So we're looking at just maybe a 1/9 or an 1/8 of the total number of drops available. So the coverage, the number of drops per square centimeter, is lower. It's absolutely lower. And that's one of the things we talked about on Wednesdays, how do you make up for that? It's with water volume. But now let's convert this to a volume. It looks like this. It's messy. Okay, so on the left side, very great drift reduction. So this would be like a dicamba nozzle for XtendiMax. And this is the large droplets. Now look at the significant amount of droplets that are simply too large to do us any good. They're large. They probably aren't hitting the target. And if they do, they may not stick to it, right? And that could be 1/3 or more of the total volume now. So we have to be careful we don't overdo it. That is a function of nozzle selection and the pressure at which we use those nozzles. Let's look at this another way. Let's look at this middle portion that I didn't talk about, or didn't color in, sorry. And here are the numbers. When we look at the drift reduction, of course, the coarser we go, the better the drift reduction. So this is the volume in the spray, less than 200 microns. If we look over at the waste, this is the volume greater than 600 microns. These are opposites of each other. But if we subtract one from the other, more or less, it's not quite that, but then we get this usable size fraction. That's the middle side. So we subtract both ends from 100 is what we're doing. And look at this. The coarse and very coarse sprays actually have the largest proportion of their spray volume in the usable size fraction. That's the reason that these low drift sprays work so well, work remarkably well, okay? And they work remarkably well for herbicides, fungicides, and insecticides, okay? So we haven't recommended a medium spray quality for many, many, many years. There's simply no advantage to going fine to get the performance out of the spray. Yes, if you have a very low water volume, and we talked about drones on Wednesday, of course, in those situations, you will have to go fine because you have a very low water volume. But if you have the luxury of having water, then you can go quite coarse. All right, let's look at some specific nozzles. I just want to run you through and catch you up on what's hot and what's not. So one of the nozzles that we use in Western Canada is the air bubble jet. I'm not sure if the air bubble jet is out east. It may or may not be. It's a European nozzle, and it was one of the first ones. These are in alphabetical order. It's one of the first ones that produced the right spray quality. So it's fairly coarse, but not too coarse. 01 to 06 size, works somewhere between 30 and about 70 psi. That's about ideal for it. You don't want to go too high in pressure with this one. It does get a little bit finer when you do. The next one is the Greenleaf Air Mix. So this is an agro-top nozzle. This is also from Europe. It's German, but it's distributed by Green Technologies in the US. This one is basically the same thing. You can go a little higher in pressure. It's a little bit coarser. Okay. Price point's also very good on this one. So this one's still significantly below $10 per nozzle, which is, I think, attractive to a lot of people. The Hypro Guardian Air, also known as the John Deere LDA, same nozzle, is in that same ballpark of droplet size. Terrific spray quality, nice wide fan angle. It doesn't go to a very large size, so only the 05, but it adds an 035, which is a brown-red color. And it's a very nice in-between size for some of those difficult to find speeds or water volumes. So it's a nice little addition. The Lechler IDK German nozzle, this is the largest manufacturer in Europe. Most European sprayers come with Lechler nozzles. Basically, it's a copy of the AgroTop. It's the same thing, basically. There's one in Saskatoon. This one's made in Saskatoon, the Wilger Combo Jet. This is a great nozzle. They have their own connector, and it's not air-induced. This is the first one in this group that is not air-induced. Makes it suitable for pulse width modulation. We'll get to that in a minute. Wide variety of droplet sizes, wide variety of flow rates, wide variety of fan angles. It's probably the most versatile of the tips because they've done a complete matrix on all possible combinations of what I just said. TJet is in there. It's not quite alphabetical. TJet should have been before Wilger, but TJet makes the AIXR. So it's the same as the previous 3 air induction tips. It has a large size range now, recently expanded, works at 30 to 90 psi, coarse to extremely coarse. You can get it down to medium with the smaller sizes and the higher pressures. So any of these nozzles, I think, would be very well suited. John Deere makes another one, or Hypro, that's the ultra low drift, made by Hypro. It's called ultra low drift for both John Deere and Hypro. This is a very low drift tip. So this is a terrific tip if the wind is high. It is one of the best drift reducing tips out there. It is a little coarse, so it'll go even to ultra coarse. It'll actually be compatible with XtendiMax traits, or Extend traits with XtendiMax herbicide, and can be used, as I said, in pretty high pressures. Now notice none of these nozzles go below 30 psi. So the traditional thinking that we can go to a low pressure is okay is actually not okay. Sorry, I've accidentally pressed the back button. All right, TJet does have a couple of other interesting nozzles. These are twin jets. These are not air, this one's not air induced. It's a nice wide fan angle. I didn't use the turbo TJet, its older cousin in here. This one has a slightly better pattern, so we prefer to use it. It can go to lower pressures. Nice wide fan angle. And lastly, the air induced version of this. This is coarser, but surprisingly, it will be compatible with PWM. So it's one of the few air induction tips that is compatible with pulse width modulation. So we've got that going for it. The most fundamental thing you need to do with a nozzle selection is to size it properly so that you are using it at the right pressure. That's our goal, to use it at the right pressure. It's not just about the nozzle, it's the pressure that also matters. So I'm going to give you a little exercise. I'm going to ask you, if you want to do 10 gallons per acre and drive 14 miles per hour, you may or may not agree with these numbers, but they're the ones that I have an example for. What nozzle size should you use? Okay, let's quickly go through how this goes. So on this table, you will see at the top here, you see US gallons per acre. Sometimes this is miles per hour, but the numbers are the same, right? These are basically travel speeds. On the left side, you see the nozzle size and the pressure and the flow rate. And the body of these tables then contain miles per hour. If this is gallons, if this is miles per hour up here, then these are gallons per acre. The numbers don't actually change. You can actually mentally switch them if you prefer one arrangement to the other. In the US system, that's always going to work for you. All right, so first thing we do is we go to 10 gallons per acre. That's the column we're looking for. And now we're going to go down that column. We're going to look for what? We're going to look for 14 miles per hour. We find it with the blue nozzle at about what? That looks like to me about 100 PSI, right? We're going to go to the next one. We're going to get 14 miles per hour across at 60 PSI. We're going to get, again, on the third example, pretty well at about 35 PSI for the brown nozzle. Which of these three do you choose? The red one, yeah, that's right. It does depend to some degree on, you have to kind of know your nozzle as well. I mean, there are some nozzles that may need lower or higher pressures depending on how they're designed, but let's face it, for the majority of the air-induced nozzles that we talked about a minute ago, the 60 PSI solution is the perfect one. It gives you two features. A, it's operating at its sort of intermediate pressure, which means the droplet size is going to be average for that nozzle. And secondly, it gives you room to move. So now, for example, this pressure range for this red nozzle is here, and then this box here is your travel speed range. So that means if you needed to slow down, say from your 16 to 10, you would still be at an acceptable pressure, 30. It'd be coarser, of course. And vice versa, you can speed up a little, should conditions be good or you're in a rush, going downhill, then your pressure can go up. And you need that travel speed flexibility for a non-PWM based system, right? And also, should conditions change, let's say it's breezy, you're doing the outside round, you lower your pressure, and you can do that. You have room to do that, and then your spray will get coarser. And when people ask me how fast should I drive, like I don't pass judgment on how fast people drive, except to say, you should drive at 60 PSI, right? So it doesn't matter to me how fast you drive. What matters to me is what pressure you generate. And when that's linked to your rate controller, you should drive at that pressure. If you don't like that travel speed, then you've got the wrong size nozzle or the wrong water volume. Make that change and keep your speed reasonable, okay? All right, or keep your pressure correct is what I mean. Pulse width modulation, just a couple of words. Who's using PWM or have customers with PWM? It's quite widespread. In my world, all case sprayers, 90% of John Deere sprayers, 50% of New Holland sprayers, and about 40 or 50% of the remainder are PWM. Our installed base on PWM is over 60% right now, across the board. New sales, 75% PWM. So that is a reality. For those of you who don't know what this is, right here we have a solenoid valve that has replaced the diaphragm check valve. So it's a shut-off valve. It pulses though, okay? And this is the solenoid. Inside of it, so a solenoid is a magnet. Inside of it has a poppet that's spring-loaded, and the magnet pulls the poppet back. So with no power, that poppet seat here, that rubber portion, rests against this here seat and seals the passage. So it's shut off. It's a shut off. So it's normally closed. No power, closed. NC. Okay? And when you apply a voltage, the magnet is activated, pulls it back, opens it up. Now you do this 15 times per second. This is 15 hertz right here, live, and I'm going to slow it down. So now you can see that valve, when it's touching my finger, it's closed. It's mostly open, right? Mostly open. Now I'm going to change the dial, and I'm going to make it mostly closed. See that? The frequency is the same, but the proportion of time that that valve is open has changed, and that is linearly related to flow rate. So now you have flow rate control without pressure change. So now you can dial in the pressure you like, and it'll stay there no matter what your travel speed. You change your travel speed, you change your flow rate needs, it changes the duty cycle, which is what I'm showing here. That's PWM. Also gives you individual nozzle sectional control, gives you turn compensation. It has a lot of features, and it's popular for a reason. Nozzle selection is very key for this. If you don't do the nozzle selection right, and in this case we got an example here of a large nozzle, 10 gallons per acre, 50 miles per hour, running at 60% duty cycle, 10 hertz, 21-inch boom, you get complete coverage. So alternating nozzles shut on and off beside each other so that they cover each other. If you do it wrong, you have a problem with overlap. So you have a too narrow a fan angle, too low a water volume for that size nozzle, therefore too low a duty cycle, maybe even too low a boom for that matter, but no judgment on that. And you can see this checkerboard is what we call it. And that shows up. If you make this mistake, this will show up. It particularly shows up with growth regulators on cereals. Shows up very strongly, checkerboarding. So make sure you do that right. What are the nozzles? The Wilger nozzle is the nozzle of choice. Case nozzle bodies are Wilger compatible. Everybody else uses this adapter ring that's here. That puts it on a T-jet lug. Otherwise, works terrific. Okay. I already showed the AI TDJ60. That's air-induced. This is a very popular one as well for T-jet models. The John Deere version, they've developed a nozzle called the LDM, the Low Drift Max. This is a ULD. It's basically a very coarse nozzle that should be used at higher pressures because it is that coarse. I don't like it at the higher flow rates because it's simply a little bit too coarse. And then on Wednesday, we had a question about the 3D90. This is a 3D nozzle. It's an inclined angle of 40 degrees coming out, and sprays a fairly fine spray, to be quite honest. I think it's too fine. I haven't actually been recommending it. I think if you're used to an air induction tip, if you move to this tip, you would have to use it at quite low pressures to have an acceptable amount of drift protection. Another option is the Guardian, the LDX nozzle. And this one is a little bit coarser than the 3D, but not much. And I would say you can use this one, but only in the largest droplet sizes, so at largest flow rates. So if you're doing 10, 15 gallons per acre, you would use the 06, 08 size nozzle. That is suitable, and you can still get a coarse spray out of it, as long as you don't go over 40 or 45 PSI. So those are some of the limitations of the system. If you want to read more about it, we have articles galore on PWM and nozzle selection on Sprayers 101, okay? Overlap. So this is, we found, instead of droplet size being a really important criterion for the performance of herbicides, we found overlap to be the new criteria, okay? And it's quite interesting because initially, nozzles were always recommended to be used at about 50% overlap. That was sufficient for a uniform pattern. But with low drift nozzles, we found a very strong relationship between the position of the spray pattern, so the position of are you at the edge or in the middle of the pattern, and droplet size and droplet number. And the little U-shaped graph here documents droplet numbers that we've measured in these patterns. So we tended to find the largest number of droplets, the highest abundance, in the middle of the pattern, relatively low amounts of droplets at the edges. So if you only have a 50% overlap, perfectly good for volumetric distribution, you have a deficiency of droplet numbers in the center, in the overlap region. And you want to avoid that. So we are going to 100% overlap as a general recommendation. You basically, the pattern width should be twice your nozzle spacing. That projects the edge of the fan into the center of the adjacent fan, and that intermingles the large, relatively scarce drops with the small, relatively abundant drops. And that's kind of where we want to be, and that's essential. For pulse width modulation, we don't recommend 100% overlap, we recommend 200% overlap. So this means that your pattern width should be 3 times the nozzle spacing. That means your boom might have to elevate a little bit, okay? So that's because they alternate in their on cycle. So here we have an on cycle for the 2 nozzles that are currently on. They're not 20 inches apart, they're 40 inches apart. And they have to still overlap by 50%. That's why 200% overlap. And then when they're done, the adjacent 2 come on, and so it goes. If you have a very low duty cycle, there are moments in time when both of these are off. That's why we want to avoid low duty cycles. But at a reasonable duty cycle, 70% say, they're usually on simultaneously for the most part, okay? So speed is one of the biggest things that I'm fighting in terms of good application practice. we have long known that good things happen when you drive slow and have a low boom, and bad things happen when that's not true. And the first time that became apparent was, well, it became apparent long before that, but the most, I think, convincing argument that we found for it was really the drift behavior. So if you look at the pull-type boom here, this is a flexi-coil boom, a sprayer that's no longer manufactured. Unfortunately, we don't manufacture pull-type sprayers in Western Canada anymore. We put a medium spray quality on here, and if you look at the bottom axis, that's a wind speed. Unfortunately, that's in miles per hour. And on the y-axis, we have drift, airborne drift, that was measured through towers. This is what it looks like, and it always looks like this. And we are seeing about, 2 to 2.5% drift at about 12 miles per hour, which is our 20 kilometer per hour wind speed. That's a nice calm day in PEI, is that correct? Certainly isn't Saskatchewan. I think we do have something in common. When we put an air induction tip on here, we reduce that drift by a factor of 4. Field data. It's magnificent. And although this is not exactly one of the nozzles I showed you, the nozzles I did show you will behave relatively similar to this. This is extremely coarse. The nozzle I showed you will be more very coarse. Okay. Now, when we go to a high clearance sprayer, and that's really the wholesale conversion has been in the West has been to high clearance sprayer, traveling faster and having higher booms. So the 14 mile per hour and 30-inch boom, very common. 16 mile per hour, very common. What's happening? So now let's put a typical high clearance sprayer nozzle on here. That's the Turbo T-Jet. And it's a coarse spray. What do you notice about the shape of this curve? It's exactly the same as it was before. Now let's put a low, even though that's a much coarser spray. Now let's put a low drift nozzle on here. This is as coarse as we can go. Our reduction in drift was by a factor of 2. And we will probably never again go back to this. Why? High booms and fast travel speeds. And if somebody approaches me and says, Tom, I'd like to find out what nozzle I can put on my sprayer so I have very, very low drift with my high boom and fast travel speeds, I say, I don't have such a nozzle. You have to lower your boom and slow down to do that. You can't ask the nozzle to do that for you because you'll suffer coverage and other issues. So I think that's really what we're up against. Technology has made it more difficult to do a good job. I'm afraid so. And it costs more money to do it as well. Okay? So we wanted to explore this a little further, and we went out with the Canola Council and got some money for some patternation work. And this is these are strings. These are whippersnipper lines. We bought about 2 miles of it. And 2 millimeter monofilament is what it is. And that's actually an international standard for collecting droplets, believe it or not. It's used in wind tunnels across the world. Slightly more expensive versions of this. And we strung it across a field, and we drove. And the reason we like this, it's a non-destructive sampler. We can drive over it with a wheel, and it'll bounce back. It's 4 inches above the ground, bounces right back up, collects the spray. So we drove this way and that way and collected the spray and found a lot of interesting things. So here's one thing. So I'm only going to show you 2 things. The one is this overall variability. Remember on Wednesday, if you were here in the evening, we talked about drones, and we showed you patterns of drones, and we said, these patterns aren't very good. Well, guess what? Spray patterns from high clearance sprayers with a medium spray quality that are traveling fast at high boom heights aren't very good either. It's better than drones. But if you look at the average lines I'm drawing here, this is the average deposit, the solid line here. We're over 50% below average and sometimes 50% above average across the width of this pattern. And I was going to put other pictures in here last night, and I reviewed my database. I have about 80 of these, and we did 80 runs. This one is actually not that bad in the big scheme of things. But one thing we did notice, so the wind's coming from the left at about 20K. We did notice a consistent signature of the wheels and the tractor unit where we had lower deposits. The wheels, the lugged wheels, and these are often 650s or 700s, are really pushing a lot of air, okay? We noticed that sometimes in the lee, although this is not as prominent here, we do have a different situation than we have in the upwind. And this is just the turbulence of this tractor unit, which is quite big. This is an R4045, okay? This is what we did when we went, so this was 17 miles an hour, 30-inch boom height. This is 7 miles per hour, okay? And we lowered the boom to 24 inches. It's better, but it's still not as good as I would like it to be. You know, so if we would have maybe gone to a coarser spray, we did a medium spray quality on purpose because we wanted the spray to be, you know, moving in turbulent flows because we were trying to measure turbulence. Yeah, so still the wheel tracks have a significant signature here, even at that slower travel speed. They just simply are aerodynamically complicated and difficult to manage. We hired PEI, which is an engineering firm, Crown Corp in Saskatchewan, to do some computational fluid dynamics. Formula One race weekend, right? Saudi Arabia this week. They do CFD to do their aerodynamics of their cars. Well, we do it on sprayers too. And it's really interesting what we found. I mean, you know, the flow field behind this simulated sprayer here is turbulent. And it's more turbulent than we thought. And for example, you can look at, you know, boom components here, hinge points, you know, tubing that are quite turbulent. The wheel here, quite turbulent, right? And even components on the boom contribute to this turbulence. And small droplets are going to be susceptible to that. It's another reason to go coarser. It's also certainly a reason to slow down. And I want to now close by talking about logistics, because that's how you slow down. You don't just slow down. You have to make up for the lost time. Now, in the first case, when we do logistical measurements, we're not finding that slowing down loses you a lot of acres per hour. That's the first surprise. You can slow down by about 25 to 30% and lose only about 5% of your productivity. Why is that? It's because, think of rush hour traffic. If you're the fastest car in rush hour traffic, the red light will stop you, and the slow traffic catches up to that car. What's the great equalizer in spraying? Filling, transporting, and frankly, turning in this country, right? Folding up your boom to turn at a headland. That's the time waster. So a fast travel speed doesn't actually gain you that much, but minimizing that downtime, that gains you something, and it's profound. We found that even the simple act of changing your filling time from, say, 25 minutes to 10 minutes, which you can do with a good tender system, boosted your productivity by 25%. So the 5% you lost by slowing down is now a 20% gain by staying slow but speeding up your filling, just the filling. Now, I am assuming a turn that doesn't include a fold-up, and I'm also including a larger field size. But even for Ontario scale fields for which we've recalculated these numbers, the savings are very similar. So this is southern Saskatchewan, so I don't want to give you false impressions here, but we used 8 R4045s with 450 engine hours per year on average. So even though, like I know in potato land, you do spray your potatoes at least a dozen times a year, I understand that. We spray Western Canadian fields on average of about 4 times a year now, mostly herbicides. But when you look at the engine hours, idle time and transport time comprise more than half of the time. And the spraying time is less than half. And so if we can reduce idle time, whatever we do during idle, we have something to boost this blue piece of that pie. And we basically are doing it by buying high-performance pumps. Right? The most important contributor to improved sprayer productivity in Western Canada is a 3-inch pump pumping 440 US gallons per minute. Believe it or not, it has nothing to do with the sprayer. So this one will do 370 in a system. By system, it means a suction and pressure line attached. This new Banjo will do 515. It's also on a 13-horse Honda. Honda is not sure whether they'll approve it for that yet. but it has potential. So, when you're filling that fast, you want to make sure that when your tank overflows and you panic, you don't slam the pressure side of that valve shut, because it'll blow your housing onto your neighbor's field, okay? So you do have a hammer on these, a very strong hammer. But this is the best-selling piece of spraying equipment in Western Canada right now. If you're not making these on your own farm, you're buying them. And this little fiber unit will cost you somewhere north of $100,000. It'll haul 10,000 gallons, and it'll fill your sprayer in 7 minutes. You have to have someone to drive it to the field, so, okay. It's a large piece of equipment. I understand where I am. But here's one thing I want to show you. When I looked at it, I said to the guys, why do you have this large port here? And they said, that's a 6-inch port. I said, what? What for? What for? Like, are you pumping 6-inch? Are you a 6-inch pump? And they said, no, actually, what we do is we accumulate our spray water in a large 40,000-gallon tank, like the liquid fertilizer holding tanks. And we use 6-inch lay-flat tube. And 6-inch lay-flat with head pressure from a tank like that will flow at 1,000 gallons a minute. Surprised me a little to hear that. Because when our guys have sprayed their 10,000 gallons and need to refill that tender on a good spray day, that tender's gone for 2 hours. If the weather's good, your spray day's over. And you've wasted those 2 hours, right? So that's the key. You want to be able to do that fill quickly as well. So one fellow that I dealt with, he puts tanks on the remotest parts of his land. He doesn't, he actually doesn't have a tender. He does it by himself, but he does hire someone to keep these tanks full of water. And then when he only has to drive to that tank. Okay. This is another way of doing it. The handler has a hot batch system. This is made for aircraft, but it works for ground as well. So this is about a 200 to 300 gallon tank here. I don't know exactly what the size is. You pre-mix your chemicals, and then when the sprayer comes in, you just transfer them over, top up with water, right? So they've had a chance to hydrate if they're dry, and so on and so forth. This is the ultimate hot batch mixer. This is a blend sprayer tank that was bought on surplus. And you basically already have a sump, an agitation system, easy clean out, stainless steel. That's where you mix your hot batch, and that's what you transfer over. It's the same size maybe as the sprayer tank that you own. So these are some of the good ideas I come across when I talk to farmers. Okay. Lastly, I wanted to show you, we talked, I think Dan McEachern, was it, that showed on the corn seed size project, Windy. Windy is great. I use Windy as well. And this is yesterday, this is last night. So that's the wind we had on PEI, and you can actually slide it to look at what the wind's going to be like tonight. So that's the wind tonight. Oh, easterly, okay? And you can keep sliding it. I mean, it only has so much utility for forecasting, but you can see that the wind has changed and will change again. And so this is something that I like to use for my activity planning. It's not, it's not empirical. It's based on models. You can zoom in and out as far as you want and see what the weather's like elsewhere. And because we know the jet stream moves from west to east, you can kind of see approaching systems this way. And I think Dan used it for sulfur emissions and this and that. It does the temperature of the Gulf Stream. I mean, it does it all. I mean, if you're going to go on Windy, have yourself a beverage and some time, because you're not going to go off Windy right away. It is actually one of the funnest things I've ever done. But it's a good planning tool for your weather. Where is it going to be windy? When is it going to change? You have a good idea about that, right? Okay, Spurs 101 is your friend. We want to help you. We have nothing to gain from it. Jason and I do this just out of our own satisfaction. So please use the website for your purposes. I want to thank Margaret and Heather again for the invitation to be with you this week. It was great. actually fun to be storm state a little bit as well. So I'm done. So if there's any questions, I'd be happy to entertain them.
So in the previous presentation, Dr. Shaftsman commented on a nozzle with a forward-backward spray. What are your thoughts on that orientation, that setup?
So 100% agree with what he said. We do it slightly differently in the West, not because it's better, but because that's just the cultural difference that we have. So Art and Dave and Helen Spicer did these, had this idea with the turbo flood. Definitely angles improve fusarium head blight head coverage, okay, head coverage. Wider angles are better, so this turbo flood idea is very good. Lower booms are necessary because you do want to make sure you don't allow the droplets to fall basically into a vertical because they're too. Core sprays are important because it's for the same reason. But we use twin fan nozzles out of the box, basically, and that's what we do. Maybe we're forfeiting a little bit of efficacy on that front, but I would recommend, if you have FHB, that you must use an angled spray, absolutely. Fantastic. Well, thank you very much.